Okay, hello everyone. My name is Zheng. I'm currently a postdoctoral research fellow at the University of British Columbia in Canada. And in this video, I'm going to talk about the mutual coupling effect in RIS-Aided communication. And this is work that I've done when I was a PhD student at Cambodia University of Science and Technology in Saudi Arabia. And this is also joint work with Ricky Wang, Professor Shamim, and Professor Al-Naffouri. So, beginning, let me briefly introduce what RIS is. RIS is a reconfigurable intelligent surface, which is also known as intelligent reflecting surface or reflect array antennas. It's a kind of array of reconfigurable scattering elements that can change the amplitudes and phases of the incident signals. So here I show a prototype of RIS that was fabricated by Cost Impact Lab. And this is a prototype that can operate in the millimeter wave band, and this work will be conducted based on this prototype. And basically, in RIS-aided communications, we often consider such a scenario with a direct path from transmitter to receiver, and as well as a RIS reflection path. And mathematically, this transmission process can be described in this form. So here we use X to denote the signal transmitted as transmitter, and this Y to denote the signal received as receiver. So you'll notice that here we have three channel matrices. So here this HIT denotes channel from the transmitter to RIS, and this HRI denotes the channel from RIS to receiver, and this HRT denotes the channel from transmitter to receiver directly. And another important component here is this matrix gamma, which is RIS response matrix. And you can see it's a diagonal matrix. So each of its diagonal entries is a response of a race element. And this response consists of amplitude response and phase response. So this is the most commonly used model for race-aided communications. But if you look at it, you will find there is an implicit assumption that assumes every race element reflects signals independently without mutual coupling. So you might ask, what is race mutual coupling? The mutual coupling itself is kind of an electromagnetic interaction between the nearby antenna elements. That means each antenna will induce currents in its neighbors, and this induced currents in turn will re-radiate and modify the effective signal seen at each antenna port. So here we show a four-way simulation of three race elements in our prototype, and we only activate this one at the corner. So you'll see its color is changing, which stands for the surface current generated on it. But it's interesting that even though we didn't activate these two elements, surface currents still appear on them, right? This is due to the mutual coupling effect. These are the induced currents from this element. So now the question is how to describe this mutual coupling effect in race communication channel model. So basically now we already have a convention model, but this model doesn't account for the mutual coupling. So to incorporate mutual coupling, we can use such a model. So basically here we only care about this race-related part. That means we can replace this part with this new model to account for the mutual coupling. And this is a model that we derived based on microwave network theory. And in this video, I don't want to go into too many mathematical details. So um, if you're interested in how we can derive this model and why it looks like this, maybe you can read this reference one for some clues. So here we just simply use it. And then you'll find a new component here is this matrix S, which is called scattering matrix. So each of its entry, Sij, denote the mutual coupling or S parameters we call between the ith element and jth element. So it's defined in this way. So we can activate this jth element, use a voltage Vj input, and measure how much voltage has been induced as ith element. So we take the ratio to uh, to be this as parameter. And it's important to note that in this process, we have to make sure all the other element in this race has zero input. So this is the definition of scattering matrix S. And we can see that if we start this S matrix as 0, it reduces to the conventional model, right? If this is 0, that means there is no mutual coupling. And this inverse, that is gamma itself. So this becomes this conventional model. There is also another interesting interpretation of this model using Newman series expansion. So under certain conditions, you can express this nonlinear model into this form, which is summation of infinite series. So if you look at the first term here only, that is a reflection. That means signal come is reflect out just the same as the conventional model. But if you look at this second term, that means when the signal come, it will be reflected out, and this reflected signal will induce current and voltage at its neighbors. This is called scattering or mutual coupling. And the scattered energy will also be reflected again. So this is described by the multiplication of these three matrices. And also this process is repeating, but also getting weaker and weaker until infinity. So even though this is the essence of mutual coupling, that is multiple times of reflection and scattering. So now since we have this model, we are interested in how to use it. So before we can use it, there are two key questions. The first one is this model correct or accurate? So here we just adopt a thought of chaining. So that is, we don't really need to care about if this model is correct or not, because there is no correct model in the world. All the models around, but some of them are useful. This is a very famous saying, right? So as long as this model can predict or infer what we interested in accurately, it'd be very useful, and we don't care about is correct or not. So this is how we see this point. And then another question is what are the typical values of this scattering matrix? So, in academic research, we often need to do simulations. When we do simulation, we would like to know what kind of value we should assign to this S matrix to conduct a fair evaluation of the performance with RIS mutual coupling. And to answer this question, the first idea we have is can we simulate or measure it? But it turns out this would be very hard as rays is excited by the EM waves in the space instead of a physical port. That means, again, based on definition of S parameters, we need to activate one of the race elements and measure how much voltage has been induced as its neighbors. And most importantly, in this process, we have to make sure all the other elements have zero input. But this is impossible in real measurement because we cannot isolate the EM waves in the space to only activate a single race element, right? Even in a full-wave simulation, it would be very hard. So based on this situation, what we can do is to estimate or learn it from what we can observe. But before we do that, we do not want to estimate every entry in this matrix S because this S might be a very large matrix, especially when we consider large scale arrays. So if we don't want to estimate every entry in this matrix S, what we can do is to first parameterize this scattering matrix. Because we already know this Sij denotes mutual coupling between element J, I, and J. And if we consider such a uniform planar array of the race element, we know these S parameters have some patterns. For example, we can think the mutual coupling between this element and this element, and the mutual coupling between this element and this element, they are the same. I do agree that rigorously they are different, but we have to make this approximation to simplify the problem. Otherwise, we have too many parameters to be estimated, right? So besides this, the second assumption we made here is that we don't consider mutual coupling between elements that are too far away from each other. As shown here, for any risk element, we only consider its mutual coupling with its neighbors and with its neighbors' neighbors. So by doing so, there are only 8 patterns of mutual coupling need to be estimated. Actually, there are 9 parameters if we include the self-coupling parameters as well. So we have additional S0 that denotes self-coupling. So based on this, we can design such a learning scheme or training scheme. That is, we assume the model is correct. We trust the model is correct and learn its parameters from data. So this is exactly the same thought as deep learning. As in deep learning, we can always use deep neural network to approximate some physical processes. Of course, we know the neural network is not a correct model for those physical processes, but as long as it can infer or predict accurately after appropriate training, it could be very useful. So here we use the same thought. So again, based on this model, and once the system is set, we can easily determine the channel between transmitter and RIS, channel between RIS and receiver, and also this RIS response matrix is none. So the only thing we don't know is this matrix S, uh, or we can say that once this S is none, we can calculate the radiation pattern of the RIS. And at the same time, we can also obtain this RIS radiation pattern through full-wave simulation. So that means based on the radiation pattern that we have obtained through full-wave simulation, we can inversely infer what this S should be. So that is to solve this minimization problem to find the best S parameters to fit the observations. Once we have estimated this S parameters, we can synthesize this matrix S. So this is the whole idea of this work. And this table presents the estimation results based on this risk prototype. And we can see all these mutual coupling parameters are actually very weak. All of them are below minus 10 dB, right? But this is reasonable as this prototype has a element spacing about half wavelength. So its mutual coupling should be relatively weak, but it still has an impact, as we can see here. So now we start to test our model and learn the parameters through full-wave simulation. So we can use our trend model to predict new radiation patterns using different system configurations and compare it with full-wave simulation ground truth. Then we will know how accurate it is. So in these three figures, we show radiation patterns of three different system configurations, which are different from those we used to train our model. So here we use black curve to show the full wave simulation, which is ground truth, and uh, we use this red dashed curve to denote the result of our chain model. And besides this, we still have two benchmarks here denoted in blue and green. So we see that especially in this figure, the chain model aligns better with full wave simulation compared to benchmarks, and this means it is more accurate. And also, the accuracy of the chain model can also be validated through experimental measurement. So here we use a vector network analyzer to measure the end-to-end S parameters between the transmitter and receiver, uh, which is denoted by SRT. And here we use two horn antennas to serve as transmitter and receiver, and we use this rays to reflect signal. Here we assume there is no multipath as they are so close to each other in this near field. So as long as we know the positions of these components, we can derive the wireless channels between them. The path loss can be calculated using free space path loss formula. And with race response and S matrix, we can predict this end-to-end as parameters. Uh, and then compare it with real measurement. So here we test the two system configurations. We use this circle to denote experimental measurement, and we use this cross mark to denote mutual coupling unaware prediction, which is the conventional model without S matrix. And we use this plus mark to denote mutual coupling aware prediction that is based on our chain model. So as we can see, the mutual coupling aware model is consistently closer to the real measurement, and this means that our model can indeed make accurate prediction. Okay, so these are the main ideas behind this work. If you interested in this topic, you are welcome to read this full paper to find more details. Thank you for your attention.